Okay, so see if we let the mystery go here. Turns out, and it's kind of, we're not going to prove why it's true. You have to look at the sort of different set of numbers, different set of arrangements of numbers than just a simple back and forward. But it turns out that this answer is related. So it's 5. You multiply that by 6, but then you multiply that by 11 and divide the whole thing by 6. Still a mystery as to what? Where did that come from? I got 5 and 6, and that sort of made sense. And then I divide by 2 because I got this. But where's the 11 come from? Why do I divide by 6? Maybe we can
So,
look at that later. But
so then it would just be 5 times 11?
right, so 5 times 11, and I do get the 55 exactly as I expected I would. The 11 comes from, it's 5, and then it's 5 plus 1, and then it's 2 times 5 plus 1, and then divide by 6. So there's a, turns out there's a nice pattern for the squares of numbers when you're adding them up that you can do this. And instead of stopping at 5, I could have stopped at 1,000, just like I did before. It would be 1,000 times 1,001 times 2 times 1,001, and then divided by 6. So the 6 stays the same. I think these are related to something called triangular numbers, but
I'm just a little confused where the 5 times 2 plus 1 comes from exactly.
right. So I'm going to just right now tell you that that's just the way it is. And then, so let me summarize on this sort of thing. So if I added up 1 plus 2 plus 3, and I wanted a general formula, then I would write continue, so this like dot, 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 until a stopping point. And the first one we did was 1,000, the second one was 5. But suppose I want a general formula. I could put an x here, but typically they'll put, for whole numbers, they'll put like an n. So you get to pick the n, and then you can use the formula to figure out what the sum of those numbers up to that point is. And so the formula is n times n plus 1 divided by 2. So let's maybe just write these down as formulas or formulae or whatever that we're not going to derive today. You know, if you want to stick around after, maybe we can chat about why these things work. We did sort of talk about why this one worked. You know, you double your thing, you get this one more, and then you multiply and divide by 2, just like Gauss did on that one. So if n was 50, you know, again, just to show, if n is 50 and you did 1 plus 2 plus 3 plus 4 plus all the way up to 50, then the answer would be 50, that's n, that's your stopping point, times 51 and divided by 2. So instead of adding all these things up, I would just have to do this very simple product, and you can do that on your calculator or something. And I know you can probably do this on your calculator, but you would get this. If I added up 1 squared plus 2 squared plus 3 squared plus, and I stopped at another point, you know, I stopped at 5 and I told you what the formula was, but you can stop at any point that you want. And it turns out the formula is, without proof on this one, is it's n times n plus 1 times 2n plus 1, all divided by 6. And again, we're not going to prove that right now, but we can look up some resources on that later if we need to, if we want to. There is one more that's like, why stop at squares if we can do cubes? So 1 cubed plus 2 cubed plus 3 cubed plus n cubed. So if we wanted to add up as many numbers as we wanted, and each one is cubed. So if we stopped at 3, it'd be 1 plus 8 plus 9, and so that would be 18. The formula for that is crazy simple compared to this one. It turns out, just to make sure I get it correct, it's this first one here, n times n plus 1 over 2, and then squared. So there's this weird relationship with the fact that if I added up numbers versus adding up the cubes of those numbers, the formula is either this pattern or it's the square of that pattern. So what? That's kind of nuts. But again, to verify that this is true with n equal to 3, that would mean 1 cubed plus 2 cubed plus 3 cubed. And according to this formula, I'd be stopping at 3. So the answer should be 3 times 3 plus 1 over 2 squared. And to see if that is correct, let's see. So that's 3 times 4, which is 12, divided by 2 is 6. And then I square that, I get 36. And
I'm just a little confused as exactly why these formulas work.
right.
I mean, I understand what they are, just understand how you came to those conclusions or how people came to those conclusions to begin with for those formulas.
Stick around after we're done with the sort of main lecture, and you can look it up and I'll show you how it works.
Okay, thank you.
But keep in mind these sort of three things as we go through, because we're going to want to go back to our example and use these to then on the back end adjust the number of rectangles we use to get a better and better approximation. So here's where things are going to look a lot more symbolic. But again, keep in mind that we've done this with one. We did this with one rectangle. It's actually a square, and we got 16. We did this with rectangles using the right-hand point, and we got 10. Then we did this with the left-hand side, and we got an answer of 10. Then we did this with the midpoint, and we got an answer of 11. Those were all with 4 different locations of rectangles, and they're all getting reasonable approximations. But if we want to do more and more rectangles to make this work, we're going to have some way to handle this large number of rectangles. So I'm going to go slowly through this because there are lots of steps to this one. But let's go back to our example 0 to 4 of 4x minus x squared. Yes. So we're back to our arch. And this is actually in example 5.3.4. We're going to do it with 16 rectangles instead. So this is going to be a challenge to even try and draw this to begin with. But we're going to do 16 rectangles, and instead of doing it all 3 ways, we're just going to try the right hand rule. The right should be safe. So, no mystery, just take your picture, maybe make it a little bit bigger here, and draw in 16 equally spaced rectangles that hit the curve using the right side. So let's try it. So 2, so write it in half. And 3, I've already done that. There's 4 different pieces there. So I got to chop all 4 of those up into 4 pieces. So there's 4, just chopping everything in half like twice here. This is the kind of thing you probably only do once in your life because you're like, this is nuts. It's a lot of drawing. And the example also does it for 1,000, but they don't draw 1,000. So let's try, see if we can do this. So we go here, on this little piece here, we go to the right-hand side, and we go up to the curve, and we make a little rectangle here. Now, what is the actual width of that rectangle there?
It's 1 over 4, right?
What is it?
1 over 4.
No. Oh, yes, sorry. My bad, 1/4, yes, 1/4. So that's 1/4 there. And it's also 1/4 there, and it's 1/4 there, and it's going to be 1/4 all the way across. So all of the widths have 1/4 as the width of their rectangle. So really, if we could figure out the heights, then the areas would be easy. It would be the height times 1/4, the next height times 1/4, the next height times a quarter, the next height times a quarter, all the way across. So let's see if we can do this. So we go to a half, we go up, we square it off for that little piece, and there's our next one. Do it again. Hopefully you're doing this on your end a little bit cleaner. Go up, over, and then down, go up. Yeah, that one was ugly. As the lines get longer, it's harder to draw. There's the next one, where we got 6 of them. 7, and then 8. And if there's any justice in the world, there's going to be some symmetry to this. We'll see. We go up. We do it again for 2.5, for 2 3/4, 3, for 3 1/4, 3.5, 3 3/4, and then the last one is 0. All right, now the fun begins here. The height, maybe right, height number 1. So first rectangle over here, height number 1. We have to figure out what this point is up at the top. But all these points we get from the equation y equals 4x minus x squared. So we take our x value, which is 1/4, and plug that in. 4 times 1/4 minus 1/4 squared. And I'm not going to work all these out right off the bat. You can, off to the side. Then I'm going to be trying to be sneaky here and see how sneaky I can get. Height 2, what's the x value for height 2? What x value am I going to plug in to figure out what this second rectangle height is?
0.5
Right, half. But here's where I'm going to be a little bit sneaky, is it's a half because it's a 1/4 and then it's another 1/4. So I'm going to have 2 copies of a 1/4. And then I'm going to have 2 copies of a 1/4. There we go. So really I've plugged in a half into the parentheses, but I've copied it in as 2 copies of a 1/4. And we'll see why as I go through. There's no reason you would know to do this, just it's a nice way to arrange the pattern. All right, H3. So what value is the x we're plugging in for the third height?
3 times 1/4.
There we go. So we have 3/4. So I'll go 4 times 3 copies of a 1/4, or 3/4. And this will be 3 copies of a 1/4. I'm just plugging in the same thing in both cases because it's x, 4x, and x squared. So those will look the same. The fourth one, well, nice thing about the fourth one is we're at 1. So we go 1, 2, 3, we're at the 4th right-hand point. We can plug in 1. But I'm not going to plug in 1. I'm going to plug in 4/4 just to keep the pattern going. I'm going to plug in 4/4 there. Yeah. Hopefully you can see the pattern. This is always 4, and that comes from the formula. I've got minuses. I've got squares on all of these things, but the thing on the inside is the same, and it has to be the same because it's x. X and x, x and x, x and x. So I'm clearly running out of room, but I have height 5, height 6, height 7, all the way down until I hit height 16. So height 16, you know the answer is 0 because I can see it from the picture. I don't go up at all. To continue the pattern, I need a 4 here, I need a squared thing here. But then what's the value of x that I'm plugging in? What is the x value I'm plugging in?
Oh, it's 0.
16 times 1/4. I mean, that's what the pattern we're going on, hasn't it?
That's right. So yeah, the height will end up being 0. That's true. But the x I'm plugging in is 4. And you can see it right in the picture. That's the point where x is 4. But to continue this pattern, I plugged in 1 quarter, 2 quarters, 3 quarters, 4 quarters. This would be 8 quarters, 10 quarters, 12, 14. I'd be plugging in 16 quarters. Correct. And since x is in both cases. I'll get that. So those are all the heights, and there's the width. So all I got to do is multiply all those things by a quarter and add them up, and that would be the area of all of these rectangles. So width times height 1, width times height 2, width times height 3, area 1, area 2, area 3, all the way down, and that would be the deal. But let's see if we can be sneakier about this. On the next slide here. So I know that the total rectangle area is the width times height 1 plus the width times height 2 plus the width times height 3 all the way across until I get the width times height 16. Or, being nice, I can use the distributive property backwards to just say, well, that's the width times, and I can just factor it out. If I factor out W from all of these things, I've got H1 plus H2 plus H3 plus all the way across H16. If you wanted to, factor it back out by distributing WH1, WH2, WH3.
I just I kind of thought of something recent. I just kind of thought of something. It
Yeah.
doesn't have to do with the total known area, but has more to do with left hand, and right hand rule.
Yeah.
Why exactly do we need both of them? Why can't we just only use one since they both equate to the same answer?
If the graph doesn't quite have the symmetry, the left and the right areas could be different.
Well, by how much exactly? Like a small amount or significantly?
It depends on the number of rectangles.
Okay.
Yeah. I mean, you could certainly do it where the left-hand side could give you 1,000,000 and the right-hand side could give you 0. Because of the rectangles lining up perfectly, lots of stuff could cancel out. I don't think we're going to see any like that. But in this particular case, yeah, left and right are the same, and that's just because of the symmetry of the graph. But if it was like really funky, you're going to get something different. But if you have 16 rectangles in there, they should be pretty close, and it should be pretty close to the midpoint.
Okay.
And I don't know if you see it coming, but we're going to do this for 16, then 1,000, then 10,000, then 1,000,000, and we're not going to write all this stuff out. We're going to want to come up with some pattern, and then as we get bigger and bigger and bigger and bigger, the word limit, hopefully in calculus, comes into your head. So we're going to want a pattern that we can take the limit of in order to make this work. So let's see how small I have to write here to get all this in. So this is a quarter. So we know from the last slide that's a quarter. Height 1. So let's go back just real quick. Height 1 is this pattern. So I'm going to write that in on this slide. So as small as I can. 4 times a quarter minus a quarter squared. That's height 1. Height 2, copying that from the previous slide, is 4 times 2 copies of a quarter minus 2 copies of a quarter squared. So that's height 2. Those two things put together. Try to write this down a couple more. 4, I got 3 copies of a quarter minus 3 copies of a quarter squared And then the last one is 4 times 16 copies of a quarter minus 16 copies. 16 copies of a quarter squared. So all I gotta do is add all that stuff up and then multiply by a quarter and I'll get the answer. But I don't want to sit at my calculator and go this minus this plus this minus this plus this minus this. And I certainly want to do it if I change this to 1,000 right now. So we got to come up with some clever pattern. So the idea is going to be taking the things that don't have the square on it and putting them all together. So just reordering. So I'll have 4 copies of a quarter plus 4 copies of twice a quarter, so that's that one, plus 4 copies of, or 4 times 3 copies of a quarter. And if I keep going, it would be 4 times 4 copies, 5 copies, 6 copies, all the way across until I hit 4 times 16 copies. And so I'm going to put a sub-parenthesis here. Then I'm going to want to subtract, if I can put this all in. Let's look at all the things that have the squares on them. So I'm going to factor this minus out of all of them. So this first one will be a quarter squared. That's this one. The next one will be the square of 2 copies of a quarter. And I factored out the minus here, so minus is in front. So I can do plus 2 copies of a quarter squared. And then 3 copies of a quarter squared. And get it in. 16 copies of a quarter squared. I might miss a parenthesis there, but good. So if you reorganized all that, you can see it's the first one of the first term, this group, the first one of the second term is H1. 4 copies of a quarter, quarter squared. And then 4 times 2 copies of a quarter, and then minus, I distributed that back down. So all the terms are there, they're just organized in kind of a nice way.
So I'm actually kind of curious about the last part.
Here?
Yeah, exactly. I don't entirely understand why you're subtracting this component from the overall function over here to the left.
Why am I breaking them out into 2 pieces?
Yeah, I kind of understand factoring, but I don't understand exactly why they're necessary in this case. I just want to know.
Right. So what we're going to try and do is use those formulas with the sigma in them to get a more condensed form of it. And I noticed that some of these things have squares on them and some of them don't. And when I look back at my formulas here, then I know that when I'm adding things, when I'm adding things that don't have squares on them, I get a certain pattern. And if I'm adding things that do have squares on them, you get a different. So I'm just trying to group them to get it so I can use those 2.
Okay, I understand.
Cool. So really, it's kind of just one more step here to get the first one. So 4 times a quarter there, that is equal to 1. So 4 quarters is 1. This one is 4, and I can cancel the quarters with the 4, and I'll get 2. And then this one, I mean, you can multiply it out in your head if you want, 4 times 3, but then you're dividing by 4. So why do the multiplication and then divide back out by 4? You don't need to do that. So, but you could. 12 divided by 4 is 3, but you can also see that you can cancel when you're doing these products. So that's going to be 3. And then the next one will be 4, and the next one will be 5. And the last one here, 4 times 16 times 4, you can cancel the 4s and you'll get 16. Yeah, that looks nice. Those numbers added up. I can probably do that. Now, this one's a little bit trickier. You'll notice that if you were to write this term out, for example, you could write it as 2 squared, a quarter squared. And the next one you can write is 3 squared, a quarter squared. And the next one, 4 squared, a quarter squared. And then 5 squared, a quarter squared. 16 squared, a quarter squared. All of these things in here are multiples of a quarter squared. So if I wanted to, I could factor again. Factor out a quarter squared. Again, is there any reason you would know to do this in advance? No. You know, this is the power of Riemann and all these smart people that came before that noticed these patterns and went, oh, this makes our job a lot easier. So the quarter squared, if I factored it out of here, that would be 1. I'd still have 1 squared. That's this term here. The next term is 2 squared, a quarter squared. If I factored out a quarter squared, I'd be left with 2 squared. If I factored it out of the next one, this is 3 squared, a quarter squared. So I would get 3 squared. If I factor the next one, I get 4 squared, 5 squared, all the way across. This would factor out to be 16 squared. Now that I get to this point, I can now recognize, finally, that this is 1 plus 2 plus 3 plus 4 plus 5 plus all the way up to 16, and I have a pattern for that. Thank you, Gauss. If this is 16 times 16 plus 1, or 17, all divided by 2. That first set of parentheses there. It's kind of miraculous. The next one is minus a quarter squared, which I can figure out in a second, times, now I have a pattern. 1 squared, 2 squared, 3 squared, 4 squared, all the way up to 16 squared. So just one more time, if I go back, I can see that 1 squared plus 2 squared plus 3 squared, wherever I stop, that's my n that I use on the other side. So I stop at 16, so I would use 16 over here. 16 times 16 plus 1 times 2 times 16 plus 1. So 16, 17, 2 times 16 plus 1 is 33. 16, 17, and 33, all divided by 6. I'm going to have to do a little bit of math, but not too bad. So this is 16 times 17 times 33 all over 6. So both of those are just using the formulas that we had before. So that's kind of nice. So what does this turn out to be? We do have to do a little bit of calculation. 16 times 17 divided by 2. I do have my calculator here, so I'm going to go ahead and use that. 16 times 17 divided by 2, that is 136. So it's just 8 times 17. The next one here, let's see. Maybe we can work this out. A quarter squared, so it's a quarter times a quarter, that'll be 1/16. And then I'm going to put in what this fraction is here. So 16 times 17 times 33, and then divide by 6. So 16 times 17 times 33 divided by 6 is 1496. Which looks big, but that's okay. It's also going to be, you got to multiply this out. So divide that by 16. Running out a little bit of room, but I'll try and squeeze in maybe one more step. That's a quarter of 136 minus 1496 divided by 16, which is 93.5. So one basic little, look at all this stuff. You got all of this stuff comes down to just this one little calculation here. So 136 minus that number divided by 4 turns out to be 10.625. All right, so that's a better approximation than we had before. We went from 16 to 10 and 11 and now 10.625. And I think you're all probably like, just get on with it and tell us the answer, but not yet. You're going to have to wait to use calculus because you won't actually be able to use calculus all the way along. So let's try 1,000 on this and see what happens. But I'm not going to go through all of this stuff again. I'm just going to talk it through here. So instead of having 16, I'm definitely not going to draw 1,000. I would go 1, 2, 3, 4, 5, 6, 1,000. Now look at the pattern. I've got one copy of a quarter in each case. I've got 2 copies of a quarter in each case. I've got 3 copies of a quarter, 4 copies, 5 copies, 16 copies. I'd have 1,000 copies of a quarter. And it wouldn't actually be a quarter anymore, sorry. It definitely wouldn't be a quarter because instead of taking 1 to 4 and chopping it into 16 pieces, I would have to take 1 to 4 and chop it into 1,000 pieces. So I'll talk about more with that, what those individual pieces are going to look like. But the nice thing is this, I'm going to have my width right here. I'm going to have my width right here. So once I figure that out, then I'll be set. Along the way, it'll be 1, 2, 3, and I wouldn't stop at 16. I would stop at 1,000. Over here, 1 squared, 2 squared, 3 squared, da, 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 da. And I wouldn't stop at 16. I would stop at 1,000. So I'm going to recopy that onto the next page to just say that if I use 1,000 rectangles back in my picture, there's no way I'm going to do this. But I'd want to chop this up. I'm probably going to draw like 15 or something. But I chop that up into 1,000 pieces. If I do that, the width of any particular piece along here, I equally divide 4 into 1,000 pieces. So I just take 4 and divide it into 1,000. Just like we did before, where we did 4 and divided it into 16 pieces, I got a quarter as my width. Now I have this. In my formula for the area of the rectangles, everything just gets replaced. Instead of having a quarter on the front, I have 4,000 on the front. Instead of having 1 plus 2 plus 3 plus and stop at 16, it'll be 1 plus 2 plus 3 plus 4, stop at 1,000.
I have a question, sir.
Go ahead.
Can we just break down the 4 over 1,000 to become like 1 over 25?
Sure. Yeah, 1 over 250, right?
Yes, sir.
Right. So we'll do that in the calculation. Just kind of easy to see that it means take the whole thing and chop it into that many parts. If you did 1 over 250, it's fine. It's just a little bit harder to see. Wait, is that 1 into 250 or what? So just keep it there for just a second. I don't know if I'll have room to fit it in. I'm going to have to shrink my picture down here again. Let's try. Instead of having 1 quarter squared, I'd have 4 over 1,000 squared. So it just takes the place of that. And with the squares, it'd be 1 squared, 2 squared, 3 squared, all the way up to, we wouldn't stop at 16, we would stop at 1,000. So if I try and use my formula here, 4 over 1,000, then this one we already did. That was Gauss. So we know that the formula there is 1,000 times 1,001 over 2. The next one is 4 over 1,000 squared. And then I go back and I use my other formula, with this whole thing here, becomes 1,000 times 1,001 times, I go twice and then add 1. So that'll be 2,001 and divide the whole thing by 6. So instead of adding up 1,000 numbers there and 1,000 numbers which are all squared there, all I have to do is this fraction and then multiply the rest of stuff out. So simplify this down, simplify this down, simplify this down, square it, simplify. You can do all of that stuff in your calculator. And it turns out that on your calculator, at least up to 6th place decimal accuracy, I'm still going to put approximate, is 10.6666656. So up to that level of accuracy, if I was to come over here and draw every single little rectangle I possibly could in there and draw 1,000 of them, they're going to fit pretty well. So I'm not going to draw all of them. You fill the entire thing in with these teeny, teeny, teeny rectangles. The overlap and the underlap almost cancel each other out, and you get down to just this here. Well, that's pretty cool that you can do this without any calculus, just a lot of algebra, and some nice little formulas that popped up along the way. So that's what the kind of stuff that you're going to do in the homework. Instead of sitting here and staring at this, I think it's probably wise to let you guys go, and we need some time to answer questions about homework anyway. So that's a good place to chop it. The homework from 5.2 is due at 1 o'clock. You can stick around and we can work on those, and then the homework for 5.3 here is due tomorrow at 1. So again, hit the accelerator and away we go. So, if you want to stick around and answer questions or talk about questions, that's cool. If you want to go, hang out the rest of your day and do homework anyway, we can do that. So maybe 2-minute break, and then whoever's left, we can work on homework together. So let's do that. We'll see you in a couple minutes.